Hello everyone. Now let us start with the next type of problems in conjugate beam method. Okay, so the next type is determine the maximum slope and deflection and take, now in this time they've given you the value of EI. So both put together E and I is equal to, EI is equal to 10,000 kilonewton meter square. So as it is, our load is in kilonewton and distance is in meter. So we'll keep this in kilonewton meter square only. We will not simplify it to the least, that is in Newton and mm square. So we'll keep it in kilonewton meter square only. Okay, so here is, it's a ABCD beam wherein AB has only EI and BC has 1.5 times EI and CD has only EI value, which are spaced at a distance of 4 meter every 4 meter. So every third 4 meter there is a load placed. Now you can see here, this is 6 kilonewton acting at B, and let's see there is another 6 kilonewton. So basically A, B and CD are having only EI values, and BC has 1.5 times EI. Okay, so again it's a symmetrical problem. So if you cut the section anywhere, if you cut this section exactly at the center and you flip it over, it will become a symmetrical section. So once you draw this given diagram, the next step is draw the deflected shape of the beam. Of course, deflection is maximum below the point loads here. Okay, below the point load, 6 kiloton B at B and 6 kiloton at C, and at A and B the deflection is 0 because they are simply supports, and rotation at A and D is maximum. At A and D is maximum. Okay, after this, now they have asked to find out maximum slope and maximum deflection. Okay, maximum slope will occur at A and D because they are supports, and maximum deflection will occur at B and C. Okay, so after this, draw the bending moment diagram, the simple bending moment diagram. So at A it is 0, at D it is 0 bending moment, and okay, now you can see here at B and C it is maximum. At B and C it is maximum. Okay, so now you can say this, how to remember this, because you don't know the formula to remember this. So what you can do is first find out the reactions, that is reaction at A, reaction at D. Now you can see here 6 kilonewton downward, here another 6 kilonewton downward. So you can see here total 12 kilonewton is acting downward. Now because it is symmetrical, equal and opposite forces will be acting upward. So in that case, 6 kilonewton downward here should be, it will be compensated with this portion here. To balance this, there is a reaction at RA 6 kilonewton upward. Similarly, at C there is 6 kilonewton acting downward. To stop this 6 kilonewton, there is another reaction acting at D, this portion. Okay, so now reaction at A is 6 kilonewton, reaction at D is 6 kilonewton. So 6 kilonewton upward, 6 kilonewton upward, 6 kilonewton downward, and 6 kilonewton downward. Now the beam is said to be in equilibrium. After this, we'll find out, draw the bending moment diagram. Now you can see here at B, to the left side of B, there is only one load, that is a reaction load, 6 kilonewton. So 6 kilonewton, it is going clockwise. So it's going clockwise, so it is 6 into 4. So 6 fours are 24. Left side clockwise is positive. So it is 6 into 4, 24. So that's how I'll write it here, 24. I'll mark it here, 24. At A it is 0, at B it is maximum 24. Similarly, at D, it is 0, and at C again we'll use the same logic, that is at D reaction is 6 kilonewton, and so if you see to the right side of C, so it's going like this, anti-clockwise. Right side anti-clockwise is positive, so it is 6 into 4, 24. So this is 24 kilonewton meter. So both are 24, so we'll join this like this. So this is only M over EI diagram, bending moment diagram, but we are more interested in M over EI diagram along with conjugate beam. That means along with conjugate supports. Okay, now you can see here it is a hinge support which is at the end, and there is a roller support which is also at the end. So hinge remains hinge in the conjugate beam method, and roller remains roller. That means, So when you try to draw this, so it is as good as simply support only. So when you draw this diagram, first as usual, draw the M over EI diagram with respect to the EI values now. See here, at A it is 0, at D it is 0. Now at B, okay, see here at B, to the left of B it is EI, to the right of B it is 1.5 times EI. So accordingly you have to draw the diagram. Now see here, at B point there are two ordinates. So this is 24. M or EI diagram is 24 divided by EI. Now this is to the left side because it should be divided with EI values only. The same ordinate at B, if you see to the right side of B, it is 24 divided by 1.5 times EI. So it is 24 divided by 1.5 times EI is 16 EI. So now you can see here at B, to the left side of B, it is 24 over EI. To the right side of B, it is 16 over EI. Okay, same thing. Then it runs straight. Okay, then again at C, to the left side of C, there is 1 EI. To the right side of C, there is another EI. So to the left side of C, that is 1.5. So this 24 divided by 1.5 becomes 16 over EI. Same thing at C, to the right side of C, it is only EI value. So it is bending moment 24 divided by EI value. So it is 24 over EI. So once you draw this, just join this diagram. Okay, after this, join all the ordinates. After this, this is M over EI. For this, you have to add conjugate supports. So these are the conjugate supports. So in actual beam, it is simply support. In real, in conjugate beam also, it becomes simply support as such. Same thing here also. It remains a roller support. Roller is nothing but again only one reaction. So only one reaction will be shown here. Okay, so after drawing this diagram, the next thing is check the total load on the beam. Okay, now see here, the total load on the beam is, this is a triangle. Now, all these loads, triangular load, rectangular load, and a triangle load, all these loads are acting downward like this because the load is 6 kilonewton on either side. It is trying to push the beam downward. So with respect to this diagram, now all the loads are acting downward. So there is one triangular load, rectangular load, and a triangular load. Now we'll find out the area of this. First, area of this triangle up to A and B. Okay, so area of this triangle is half into base into height. So half into base is 4 meter, height is 24 over EI. Now the same triangle, because it is symmetrical, the same triangle is over at this portion also. See, half into base 4 meter, height is 24. So what I'll do here is half into base into height. Because they're true triangles, I'll multiply this into 2. So it takes into account of both the triangles. Then we're left with rectangle. Now you can see here, this is 2 meter, this is 2 meter. So total here is 4 meter. Total this is 4 meter. So area of rectangle is length into breadth. So length is 4 meter, breadth is 16 over EI. So the total load which is acting downwards is, when you simplify this, you'll get this 160 over EI. Now, the total 160 over EI is acting downward. To stop this load, now, because it is symmetrical, we'll imagine that the load 160 is acting exactly at the center. So now, this load gets distributed equally here. To the left side, half. To the right side, half. So basically, it is 160 over EI acting downward. So when you divide this, it becomes 80 and 80. So 80 upward, 80 upward. When you add both of these, it becomes 160. Okay, so now we are going to show this as VA. So VA is nothing but the shear force. So VA is equal to 80 over EI. VD is equal to 80 over EI. Now we have to find the slope. So ultimately we have to find maximum slope and maximum deflection. So maximum slope will be theta A and theta D. Okay, so again theta A, as usual, use the formula. Theta A in real beam is equal to, again, theta is associated with shear force and delta is associated with bending moment of this particular diagram. Okay, so theta A in real beam is equal to shear force at A in conjugate beam. So once you write this formula, writing this formula is very, very important because based on this, you can just write this, formulate this. Okay. So theta A. So theta A is equal to, then check out what is shear force at A in conjugate beam. So shear force at A in conjugate beam is equal to, we have already found out this, 80 over EI. So directly write 80 over EI. Now that you have the value of EI, just substitute this. So 80 divided by 10,000 is equal to 0.008 radians. Okay. So this is theta A. And next is, okay, now see here, at B and C there are loads acting, of course. And what we'll do here is, because it is exactly at the center, see here, exactly at the center is 6 meter. 4, half of 4 is 6. Up to this, from 4 plus 2, exactly at 6 meter from the left end. Because it is exactly the center, and if you flip this over, it becomes symmetrical only at point E. So we are going to include an additional point, which is E here, and this E will get maximum deflection. So that's why we'll write it here as delta E. So delta E is the new point wherein there is a maximum deflection. Again, why when I am taking this as maximum? Because see, at B, though it is maximum, at C also it is maximum, but we'll find out at the center of this. Deflection would be always maximum at the center, exactly the center of the beam. Though the loads are acting eccentric from the center, but we'll always find out deflection would be always maximum. No matter what, it will be always maximum at the center of the beam. So at the center of the beam, it is E, will formulate. So it is at a distance 6 meter. So delta E is equal to, now again the formula is delta E in real beam is equal to bending moment at E in conjugate beam. So delta E, if you want to find delta E in real beam, is just nothing but bending moment at E in conjugate beam. So bending moment at E in conjugate beam. So delta E is equal to, now see, let's start with this. To the left side of E, there are two types of areas. One is the triangular load and one more is the rectangular. Okay, rectangular load. Now in addition to this, there is one more shear force. Okay, so there is, so if you see to the left side of C, left side of E, that is VA into perpendicular distance, area of a triangle into its perpendicular distance measured from E, then area of a rectangle into its perpendicular distance again measured from E point. Okay, so let's start this. So to the left side, clockwise is positive. So it is VA, that is 80 into 80 divided by EI, 80 into perpendicular distance to reach E. So perpendicular distance is 6. So it is 80 over EI into 6. Next, area of this triangular load. So take the area of this, that is half into base 4 meter, height 24. Now again, here don't get confused with this 24 and 16. 24 would be to the left side and 16 would be to the right side. So right now we're taking the triangle. So this complete triangle is 24. So it is half into base 4 meter, height is 24 over EI. Now next, CG of this with respect to E. Now CG distances, now see here, centroid of this triangle measured from the base. You're measuring like this with respect to E. So what you can see here is first the base of the triangle. Okay, so the base of the triangle is 1/3. So it is 1/3 of 4 meter plus 2 meter because you're measuring with respect to E. Then, so again, this is going anti-clockwise. So anti-clockwise, negative. Next, area of this triangle, which is acting downward like this, point load, we are converting this into a point load. So area of this is, again, it's a rectangle, 2 into, now it is, this is 16 over EI. So 2 into 16 over EI. Okay, then CG of this distance with respect to E. So this is 2 meter. 2 by 2 is 1. So it is 2 divided by 2. Centroid of a rectangle is exactly half. So it is 2 divided by 2. So again, when you solve this, you'll get the maximum deflection. Again, you can see here 288 over EI. Again, you have the value of EI. So substitute that value. Then you'll get this answer. And you should always be careful that with to the left side of C, clockwise positive, anti-clockwise negative. So accordingly, you have to use this plus, minus, and minus signs. Okay. The next problem is determine the maximum slope and deflection for a given simply support beam as shown in the figure. Okay, so it is a simply support beam, that is one end has a hinge, the other has a roller. So it is still treated as a simply support because see here, a roller support has only one reaction, like this upward, and the hitch support has two reactions, so upward and horizontal. But in beams, the horizontal movement is very, very considerably negligible. So we are going to ignore this and just take only the vertical reaction here. Okay. So now determine the maximum slope and deflection for the given simply support beam as shown in the figure. It is simply support beam with a UDL, W per unit length. So after this, draw as usual, draw the deflected shape of the beam. So this red mark, you can see it is a deflected shape of the beam. So deflection is maximum at the center and the rotation is maximum at A and B. Okay. After this, as it is symmetrical, because if you cut this section here and flip this over, it would still be the same. So it is symmetrical. Okay. Then the next important thing is we are going to draw the M over EI diagram. Okay. Now, see, it is a simply supported beam with the UDL. So we would draw the M over EI diagram. That is, it would be a parabolic curve. That is WL square over 8. Now be careful. W is a small w here. It's a UDL load. So WL square over 8. Because it is a M over EI diagram, so we'll divide this ordinate with EI. So at C it is maximum. Then at A it is 0, at B it is 0, and C it is maximum. And this is the length L. Okay. Now this is MODI diagram followed by the conjugate beam diagram. So because it's a conjugate beam, what we'll do, the simply support remains simply support. So we are going to replace the support with A and B. So when you replace with support with A and B, okay, so then check this out. First, total load. So take the area of this total downward load. Now, because it is a parabolic curve, so it would be the total load, the area of this parabolic curve would be 2/3. Okay, because it's a curve, 2/3 of L. Okay, 2/3 of X and Y. If you go with the formula, it is total load. If you take the complete total load, which is acting downward, this area, so it is 2/3 of X and Y. So 2/3, X is L, Y is WL square over 8EI. So when you simplify this, you'll get WL cube by 12EI. Now this WL cube by 12EI, it gets distributed equally because it is symmetrical. It gets equally distributed at A and at B. So VA and VB would be total load, total downward load acting, which will be split into 2. So I'll divide it by 2. So total load divided by 2. So it half of it is carried by VA, another half is carried by VB. So WL cube by 24 EI. So I'll write this V and VB as WL square. So total downward load is WL cube by 12 EI, which is acting downward. To stop this, there are two supports which are trying to stop this. So that's why it gets distributed equally on them. Okay, after you draw this diagram, next is calculation of theta A, theta B, and delta C. Okay, now again go with the formula, that is theta A. We know that theta A in real beam, okay, so theta A in real beam is equal to shear force at A in conjugate beam. Theta A in real beam, theta A in real beam is equal to shear force at A in conjugate beam. So shear force at A in conjugate beam is, so we have already found out theta A, shear force is nothing but VA, that is WL cube by 24 EI. So again, answer is positive, it's a clockwise. Then theta B, because it is symmetry, theta B would be just the opposite. So it is WL cube by 24 EI, theta B would be just the opposite, that is minus WL cube by 24 EI. Okay. Next, we have to calculate the maximum deflection. Okay, so maximum deflection is at C, that is delta C. So delta C is given by, now see here, delta C is given by, delta C, use the formula, delta C in real beam, see here, delta C in real beam is equal to bending moment at C in conjugate beam. Delta C in real beam is equal to bending moment at C in conjugate beam. Now, once you apply this formula, now check this out. At C, to the left side of C. Now, to the left side of C, there are two loads acting. One is this VA. So, VA into its perpendicular distance. Then, area between A and C, this parabolic curve area into its perpendicular distance. So, theta C is equal to, now write this, WL cube by 24 EI, VA. Now, VA is going clockwise. Now, because it's going clockwise, answer is, the sign would be positive. So WL cube by 24 EI into its perpendicular distance. Now, perpendicular distance is exactly half, that is L by 2. So it is WL cube by 24 EI into L by 2. Again, it is going clockwise, so the sign is positive. Next, area of this parabolic curve. Again, to see only to the left side of C. So area of the parabolic curve, because it's a parabolic curve, again, 2/3 of base. Base is only L by 2. So 2/3 of base L by 2 into height WL square by 8EI. So 2/3 of L by 2 into WL square by 8EI. Now this is the area. Then CG of this area from point C, because we're measuring from with respect to C from point C. So if you measure this like this from C to this point, so centroid is somewhere here. So if you measure from here, it is 3 by 8 times. So if this distance centroid between A and C, it is 3 by 8 times L by 2. So it is area into CG distance. Now again, this load is acting downward. So it is going like this, clockwise. This is going anti-clockwise. So clockwise is positive, which is VA. Anti-clockwise is negative. So this is anti-clockwise minus. So when you simplify this, you'll get the same answer. Now see here, again, the approach is different. The approach is different, but both the methods you'll get the same answer, that is delta C. Either you solve by moment area method or conjugate beam method. In both the methods you'll get the same deflection formula. Okay, that's it for today. Thank you.